Hello everybody, welcome to the subject electromagnetic waves and transmission lines. In the previous video we have discussed about reflection by a perfect dielectric media at normal instance. So in this video we are going to discuss about reflection by a perfect conductor at normal instance. So let me consider the incident wave is traveling from medium 1 to medium 2. So here medium 1 is considered to be an lossless medium or an air, and medium 2 is a perfect conductor. Now let the wave is normally incident from medium 1 to medium 2. In this case, when the wave is traveling in air, is normally incident onto the surface of the perfect conductor, it is entirely reflected back, as the plane wave cannot penetrate into a perfect conductor. Due to existence of incident and reflected waves, formation of standing wave patterns takes place in the air. As no losses within a perfect conductor, no energy is absorbed by the conducting medium. Now here look into this diagram. The medium 1 and medium 2 are separated by a boundary which is taken at x equal to 0. I assume that the incident wave is traveling from medium 1 to medium 2 along positive x direction. Medium 1 is considered to be in x less than 0 region, and medium 2 is considered to be in x greater than 0 region. So when the wave is incident normally to the surface of the boundary or interface, the entire wave is reflected back into the same medium, as no energy is absorbed by the perfect conductor. Hence, due to incident wave and reflected wave in medium 1 combine together forming a standing wave pattern. You can see this is a standing wave pattern of the electric field strength, and this is the standing wave pattern of the magnetic field strength. So you can see always we know that the electric field and magnetic field of the plane wave are right angles to each other. So if I consider the wave is propagating along positive x direction, I assume that the electric field is along z direction and magnetic field will be along y direction. And we can observe here when the wave is reflected back, there will be phase reversal in the electric field strength. That is, the electric field strength and of the incident wave and the electric field strength of the reflected wave are in phase reversal. Hence, there will be no phase reversal in the magnetic field strength across the boundary. So let the electric field of the incident wave is taken as EI into e to the power of j beta x, as the incident wave is traveling along x direction. This is the field strength of the incident wave EI propagating along x direction with a phase constant of beta. And similarly, the electric field strength of the reflected wave is taken as ER into e to the power of j beta x. Here, the plus sign indicates that the wave is reflected back along negative x direction. Boundary is the surface of the perfect conductor at x equal to 0. So across the boundary, the tangential component of the electric field should be continuous across the boundary. That is E tan 1 equal to E tan 2. As the electric field strength inside the conductor is 0, so the tangential component inside the perfect conductor is 0. Hence, just above the surface of the perfect conductor, that is in the region medium 1, the tangential field component will be equal to EI plus ER, which is equal to 0. Therefore, ER will be equal to minus EI. That is, the amplitude of the reflected electric field is equal to amplitude of the incident electric field. but with a phase reversal on reflection. Hence, the resultant electric field strength at any point at a distance x from x equal to 0 plane is given as is the sum of incident wave plus reflected wave. So, it is written as Et of x equal to Ei into e to the power of j beta x plus Er into e to the power of j beta x. We know that Er is equal to minus Ei. If we substitute for this, Ei into e to the power of minus j beta x minus e to the power of plus j beta x is nothing but equal to minus 2j Ei into sine beta x. And if you want to represent this in a time varying form, you should multiply with the time factor, that is e to the power of j omega t. So the resultant electric field strength in time varying form is written like this, and taking the real part of this term, you get 2ei sine beta x sine omega t. So this expression represents a standing wave pattern of the electric field strength. The magnitude of the electric field varies sinusoidally with distance x from the reflecting plane. So from the reflecting plane, that is at x equal to 0 and the multiples of half wavelength, at the multiples of half wavelength, the resultant electric field strength is 0. And at odd multiples of half quarter wavelength, the electric field strength is maximum, which will be equal to 2ei. So as a result, the electric field is reflected with a phase reversal. Then the magnetic field is reflected without phase reversal to satisfy the boundary conditions. As I told you earlier, across the at the boundary, the electric field changes its direction, but there is no change in the direction of the magnetic field component. So HR will be equal to HI. So in a similar manner, you are going to write the resultant magnetic field intensity at any point at a distance x from x equal to 0 plane is HT of x is equal to magnetic field of the incident wave plus magnetic field of the reflected wave, where HR is equal to HI. So I can write this expression as HI into e to the power of j beta x plus e to the power of j beta x, which is equal to 2HI cos beta x. So in time varying form, you multiply with the time factor e to the power of j omega t and take the real value of the term, and you get 2HI cos beta x cos omega t, which also represents the standing wave pattern of the magnetic field intensity, where at x equal to quarter wavelength or odd multiples of quarter wavelength, the magnetic field is 0, and at x equal to 0 and multiples of half wavelength, h of t is maximum, which is equal to 2HI, and hence it results a standing wave pattern. It is observed that in the above expressions that the resultant electric field and magnetic field are 90 degrees apart in the time phase, and also at the surface of the reflecting plane or at the surface of the perfect conductor, the resultant magnetic field is equal to surface current, which is denoted by K. So in next class we discuss about reflection and refraction by a dielectric media at oblique incidence. Thank you.